Now I'm going to begin section 2.2, which talks about functions. The first thing we need to talk about is what is the definition of a function. And I will tell you on your first test, you will have to answer this. What is a function? A function is a rule that corresponds each element in a set A called the domain into a unique element in set B called the range. Key things in the definition are function is a rule. It corresponds elements in the first set, and that first set is called the domain, into unique elements into the second set, and that second set is called the range. For example, I have a rule: square a number. One way to represent the function is with my set A going to my set B, and if I take the number 2, use the rule on it, square it, the number 2 in set A, the domain, becomes a 4 in the range. -1 squared becomes a 1 in the range. 0 squared becomes 0 in the range. 1 squared becomes 1 in the range. And 2 squared becomes 4 in the range. So one way that I can represent a function is with mappings between two sets. Another way to represent a function is with a name. And with that name, I typically, in math, we use short names. We don't use long names. And names that you typically you'll see is like F or G or H, typically single letter names. And if I want to say that I'm taking the number 2 from the domain and it maps to number 4 in the range using function notation, I would write it as f of 2, actually f of -2, equals 4. This says I take the number -2, perform the rule f on it, and that gives me the answer 4. Another example is f of pi. Take pi, perform the function rule of squaring the number on it, and I end up with pi squared. Except there's an infinite number of numbers that I could have in my domain if I'm talking about all real numbers. And one way that I can write it is I can write it generically with the equation of the function by using the function's name, and I use x for a placeholder, and then I write what the function actually does. So for example, this rule, square a number using the function name f, the equation for the function would be f of x equals x squared. Other functions, look at this one. If I take the rule, the square root of a number, in my two sets, if I take the number 4 in the domain, it's going to map to the number 2 in the range. I take the number 1 in the domain, it will map to the number 1 in the range. Put 0 into the domain, it maps to 0 in the range. If I give it the name g, I can write g of x is equal to the square root of x. Now let's talk about some other numbers. If I try to put number 1 into the square root negative 1 into the square root function, I get the square root of negative 1. And if I'm talking about the real numbers as my domain, I can't take the square root of negative 1. So what I could do is I could say g of 1 is not, or actually, g of 1 does not exist. And the reason it does not exist is negative 1 is not in the domain of G. So far I've showed you 2 different ways to represent functions, actually 3. One is a verbal model. The second one is a mapping in between sets. The third way is by using an equation. And I can extend on this model that we had here where f of 2 equals 4, and we can actually write this as a list of ordered pairs. For example, going back to the function f of x equals x squared, I can also write this as a set of ordered pairs. F of negative 2 equals 4 would give me the ordered pair negative 2 comma 4. F of pi comma pi squared would give me pi squared. Negative 2 going to 4 I have, negative 1 going to 1, 0 to 0. And I could make an infinite list of ordered pairs. One thing what ordered pairs kind of gives us the hint is that we could actually take these numbers as our ordered pairs and we could graph points on the equation of our function, which is the last method for defining a function.